How does post-tensioning work? To explain how post-tensioning works, let's look at this example of a concrete beam that runs over 3 columns, with 2 spans, and a cantilever on the right-hand end. To gain a better understanding of its structural behavior, let's begin by examining its deflected shape. This is an exaggerated representation of how the beam will naturally deflect under loads. It will sag between columns and curve upwards above them, which is known as hogging. Now, let's add a post-tensioning tendon and observe its effects. Typically, PT tendons are installed in a parabolic shape, similar to the natural deflected shape of the beam. This means, the tendon is profiled with a low profile in between supports, and a high profile over the supports. It's worth noting that there are limits to how much we can curve the ducts, as they are not very flexible. Therefore, while the top drape is often left unchanged, the load drape needs to be designed to suit each individual case. A good question to ask is, why do we need to shape the tendon in this particular manner? To answer this question, we need to examine what happens once the tendons are stressed. When a strand is stressed, it attempts to straighten out through the duct. Due to the parabolic shape of the tendon, this causes the strand to make contact with the bottom of the duct, over the column, and the top of the duct, in between the columns. This behavior results in upward forces being applied to the concrete in between columns, and downward forces over the columns. As a result, the load between the supports acts in the opposite direction to the beam's self-weight, or any additional loading on top of the beam. This effectively balances out the applied load, which means that the beam is subjected to a reduced load overall. This is why this load is commonly referred to as the balanced load. This behavior plays a crucial role in controlling deflections, which can be particularly challenging to manage, especially when dealing with large spans, such as 8 meters. It's important to note, the larger the distance between the low point and high point in a single span, the greater the balanced load. In practice, we typically keep the high drape over the supports unchanged, and instead focus on designing the low drape to achieve the most efficient design. For instance, this end span has only one side to counterbalance its weight, so it will work harder than the other spans. In such cases, we may higher the PT in the back span as much as possible to reduce the balanced load in that span, to further alleviate the load on the end span and help it work more efficiently. In certain cases, where a large number of tendons are used within a beam or slab, once the tendons are fully stressed, it is possible for the element to deflect upwards in between columns. A transfer floor is a good example of this, where the upper levels are not yet constructed at the time of tendon stressing. As a result, the transfer floor may experience an upward deflection caused by the balanced load. Obviously, this upward deflection, caused by the balanced load, is typically short-term. Once the levels above are constructed, the vertical loading will counteract this effect, and the final deflection will often be downwards. Another advantage of using this specially profiled PT tendon is, it can increase the structural capacity of an element. Let me explain how. Looking at the profile, we can observe that the strands are situated closer to the beam soffit, in between columns, and at the top over the columns. These zones correspond to areas where the concrete will undergo tension caused by bending. Since the strands used in this PT tendon are typically 3 times stronger than a typical N-type rebar, the use of this tendon can significantly increase the structural capacity of the concrete element. In addition, The compression force, applied during the process of stressing the tendons, also contributes to increasing the structural capacity of the PT beam. You may wonder why the concrete undergoes compression once the tendons are stressed. This is because the tendons are locked at both ends inside the concrete. And as we stretch the strands, they apply a compression load to the concrete. To better explain why compression force increases the structural capacity, think of a simple example of a series of books. If you try to lift the books by pressing them inwards, the force you apply at two ends helps with the bending capacity and enables you to lift the books. Similarly, in the case of a PT beam, the compression force applied by the tension tendons helps the concrete resist bending and increases the structural capacity of the member. Another advantage of the compression load applied during the process of stressing the tendons is, it can help reduce and prevent the opening of shrinkage cracks. Now, I have a question for you. Why do engineers sometimes choose to use flat tendons that run at mid-depth across a concrete element, rather than using profiled tendons? Well, as you may recall, since flat tendons do not have a profile, there is no balanced load. Therefore, flat tendons mainly help by adding compression force to the concrete. They are often used for crack control purposes and can reduce the amount of steel required for crack control. A good example would be the secondary direction or non-structural direction of a one-way slab. In this case, we still require some tendons for crack control purposes. But we don't need to profile them, since it is a non-structural direction. In summary, efficiency in design and enhanced structural behavior are the key benefits that post-tension concrete structural elements provide. See you in the next video. Teletraining makes the most practical content for the quality construction industry.